started.
Thank you, Marco. All right, so who's happy with compilation times in Scala? If you're happy, you shouldn't be in this talk. All right, so I'm Mirco Dotta, co-founder of Triplequote, and I've been around in the Scala community for a while, working on different open source projects. But right now, at Triplequote, our mission is to cut down on swarm fights due to long Scala compilation. So we all feel so much productive with Scala, right? But are we? Can't you relate with this tweet? Like, I love Scala, but sometimes, it just takes so much to compile. So what can we do about it? Well, we can go and, build sophisticated technology to pull us back to work. So pull us back from, our checking the tweet feeds or browsing the Facebook timeline so that we can, back to work and be productive again. But we believe we can do better than that. And this is what I'll be talking about in this talk. So we start by looking at the state of Scala releases, kind of getting an idea, is Scala getting any faster? Can we say anything about it? And then we'll actually take a dive into, okay, I feel I have long compile times. I feel that something is wrong. What can we do? What are the tooling that is available today that can help us with that? And last but not least, we look at what we're doing at Triplequote. So we have a productivity tool that allows you to compile your Scala code in parallel, with the idea that, of course, we're going to be using all the cores available in today's machine, so you can cut down on compile time for free. So let's start by looking at the Scala releases. So Scala to the 12th was released back in November 2016. And, well, my personal favorite about 2.12 is that it drastically reduces the binary footprint of our compiled code. How does it do that? Well, it takes advantage of the Java 8 runtime, right? So the Scala team has gone a long way to take advantage of this new runtime. So they have a new encoding for traits that utilize Java 8 interface and default methods instead of, the old way of encoding traits. And that brings huge benefits at the class file level because you produce way less binaries. And the same is true also for lambdas. Instead of generating these anonymous classes, which of course they need to get into binaries as well, well, we can use the Java 8 method handle and all the machinery that is available in the Java 8 runtime. So this is fantastic. This is really great, and this is why we all kind of jumped on 2.12. But what can we say about performances of the compiler? If you look at shapeless and you compare 2.11.8 against 2.12.1, well, it actually seemed like performance regressed. It was 20% slower at compiling test, 2.12.1. But if you talk to the Scala team, they were fairly happy with the release because on their benchmarks, it seemed like Scala was behaving more or less the same and maybe even slightly better than 2.11. So, from these two different points of view, we can basically say that it's very hard to assess whether the Scala compiler was getting any faster. We didn't have any objective way of, assessing that. And the good news is that, well, the Scala team sort of agreed with that, and so they started to work into automatic benchmarking. And, well, the very good news is that the upcoming 2.12.3 release is going to integrate some important performance improvements thanks to the fact that they now have automatic benchmarking, so they were able to spot regressions and compile time inefficiencies in the compiler. And so they, when I say they, it usually means Jason Zaug, but it's the whole team. But Jason definitely put a lot of effort into improving compile times. So this is great, and 2.12.3 is going to be out at the end of July. But you can try it out right away, and you can report whether it's, do you see any compile time improvements on your project? I'm sure that the Scala team would be very much interested in knowing that. So if you have time, just go ahead and give it a try and, let the Scala team know about it. But, what about our code? If the Scala team is working on automatic benchmarking, does it mean that we don't have to, care anymore because they're going to fix the problem for all of us? Of course not. We can do still plenty of wrong things in our code. We get to write implicits, we get to write macros, and if we don't know what we're doing, well, that can actually hamper quite badly compile times and as a consequence, the productivity of us and our team. So, what can we do about it? Well, we should definitely be aware of what are the tooling that exists today that can help us understand what's going on at compile time, and so detect these compile time inefficiencies. So what are these tools? Anyone? It's Scala C. Scala C is the tool. Scala compiler has a ton of flag that can help you with, well, on the one side, it can help you automatically detect code that is dead, is not used. So you can just remove it, and your program won't change. But by removing the code, well, the compiler has to do less, and so of course it's going to be faster. So the less code you have, the faster it will get. That's pretty straightforward. But of course, those are, I'd say, the low-hanging fruits that you can easily go and catch. You probably won't get 20, 30% speed up out of those. But I think those are good flags to maybe put on your CI so that you don't pay for the overhead every time you compile, but you see it on the CI, and you can kind of react based on whether you see any of those warnings well, coming up on when you compile on your continuous integration server. But what if you're actually feeling that your compile times are extremely slow and you want to do something about it? Well, then you have to be ready to go and understand a bit more what the compiler does. You need to be ready to understand, how is your code being transformed by the compiler? What's happening in, this black box? You need to open it up, basically, and start seeing what it's doing. And there are a number of flags that can help you with this. So minus verbose is, I'd say, is the starting point. If you turn it on, it's extremely verbose. But there is one information that is really useful. It gives you the time by phase that it's taking to compile your code. So as you might know, the compiler has many phases. There are actually 24 at the moment. And each phase takes, well, your code initially gets transformed into an abstract syntax tree, and every phase is going to transform that abstract syntax tree into another one until at the very end is going to produce bytecode. So your code goes through different transformations, and each transformation is a phase. So by enabling minus verbose, you can see how much time is being spent for each phase to compile your code. Then another super useful one is -x print, and then you pass the name of the phase. That shows you the abstract syntax tree after the phase that you gave in argument. And if you don't know about the phases, what are the phases in the compiler, you can use -x show phases, and that will list you all the phases. And so you have a name that you can pass to the print flag. And we'll see how that can be useful later on. -x log implicits, it gives you a trace of what are the implicits that were attempted by the compiler, but they did not succeed. Of course, the more implicits the compiler will attempt to yield your program, the longer it will take. Right? It is all work that the compiler has to do, so that's, again, useful information when you're trying to understand why is it taking so long to compile. And last but not least, there are a couple of macro flags that tells you what's happening during macro expansion. Nowadays, I'd say pretty much all of our code is somehow or some way using macros. Sometimes it can be really slow, and that gives you information about what's happening during this macro expansion phase. So, how do we start our journey? Well, we need to start by analyzing, so getting a feeling of what's happening, and minus verbose is the way. So here's what I've done with the ACActor module. On the y-axis, we have the compiler phases. On the x-axis, we have the time that it takes for each phase. And blue is the ACActor module, while green, even though you can't see it, well, yeah, no, I think it should be visible. Green is a project at Zalando. It's an internal project at Zalando. Basically, that team at Zalando, they called us because they were having a problem with compile time. And this is the first thing we did. It's like, OK, let's have a look at how much does it take to compile their project by phase. And what is the striking fact about this chart? There is that green line that is taking a lot of time, right? It's actually 32 seconds out of a total, I believe it was 54 or 56 seconds. Who can guess what phase is that? It is Typer. So typer is when, all the magic happen, and that's why we love Scala. Scala is doing, all the heavy work, but in that case, it was definitely doing quite a lot. So it was taking forever to compile. So I'd say that whenever you see that typer is taking 40% of your, whole compile time, you should know why. There may be reasons why it's taking so long. Namely, you may be using some, advanced Typelevel library, but you should know why it's taking so much time. If you don't know, or if you're unsure why it's taking so long, that's your opportunity to investigate and actually, your opportunity to cut down on compilation time in your project. So, where do you start? Well, there are usual suspects when it comes to type checking time, because at the end, what we're focusing on is type checking. Type checking is the one that can take a long time and can basically be responsible for the long compile time. And the usual suspects are macros, implicits, and in particular, implicits that are implemented with a macro, right? The two really have an interplay. Macros are a problem because they can, they're compiler plugins. They can do anything. They can, call type checking as many times as they want. And of course, the more times you type check something, the more it will take. And last but not least, also type inference. And I actually think that was a really interesting, fact that happened on the IntelliJ Scala project. Just by having explicit types, they said that they decreased their compile time by 17%. So that was quite impressive. I wouldn't have expected it, so that was definitely really good. So, one easy thing that you may attend is using Scala fix for, making all the types in your project explicit and see if there is actually some benefit, if you actually get better compilation time. So what do we do next? Now that we know that there are some, suspects, how do we go about it? Well, you need to know what are the source files that are taking the most to compile. So you need to have a guess at the moment. There is no tool that can help you with that. The good news is that we're working on it, and actually next week we're going to release something that exactly addresses this problem so that you can know what are the source files that takes the most to compile, but at the moment you don't have it. So you need to have a guess for it. And so if you think a source file is taking a lot to compile, just try to compile that single source file alone and see how much time it takes to compile. That is a really easy way to validate your thought, your guess. If it's indeed taking a lot of time, then investigate. It's great. You actually spot it. You spot something that isn't right. So go on and investigate. Go deep. So what can you do? Well, I told you before, just print the abstract syntax tree after typer. So you can use this -x print typer command line option and have a look at the AST. If it looks completely different from your code, from your initial code, then most likely there are macro expansions at play. And just to give you an idea, we have seen code where we had like 200 lines of code, and the AST was like 45,000 lines of code. And that was taking a lot of time to compile, like 30 seconds, 40 seconds. But there is no magic at the end. It was taking so long just because there was all this code that was being generated by macro expansions. And another thing that is visible when you do -x print typer is if there is any complex long type that is being inferred. You have all this information at that point in the AST because your source file has been type checked. In case none of this is true, like your AST pretty much looks like after parsing, then most likely the reason why that file is taking so long to compile is implicit resolution. And so if you turn on -x log implicits, you will get this trace about what are the implicits that the compiler is attempting, and you should kind of get an idea, is this expected? Why is it trying all these implicits? Maybe some of them, they shouldn't be in the scope. So, I did something wrong in my code. They end up being in the scope while I didn't expect them to be in the scope. So if I improve it, if I fix that, I can actually cut down on compile time. And the good thing about doing this thing on a source file is that most likely you'll see the same pattern across your code base. So when you can optimize one source file, chances are that you can actually optimize across your whole project. So it's really a huge opportunity, and we have actually seen that as Zalando. So we're talking about implicits, implicit resolution. Who knows how Scala does it? Good. So if you don't know, you should read chapter 7 of the Scala reference. It is very digestible. I would highly recommend to read it. And in fact, I'd say, let's just take a 10 minutes break. And you guys go and read it. Of course not. All right. Let's try to build sort of an intuition of how implicit resolution works. Here I have a very trivial example. I would definitely not recommend to do anything like that. But I have a show method that takes a map of ID employees, and I'm calling that method passing an employee. Of course, this won't work, right? Unless the compiler can yield that expression. And how can the compiler do that? If it can find an implicit, right? So the first thing the compiler will do is there an implicit in the current scope? So is there an implicit available without any prefix, basically, that can help me transform an employee into a map of ID employee? If we can find it, great. It will, it will just insert the implicit conversion at the call side, and and the expression will type check. It will compile, and so it'll move on the compiler. But what if it doesn't find it? What is the next step of the implicit resolution algorithm? There are actually two steps. One is what's available in the current scope. I can't find an implicit. Am I bailing out, or will I try to do something more? I didn't catch that. Yes, the imports are all parts of the current scope. It's everything that is available without a prefix. Exactly. So if the compiler can't find an implicit in the current scope, it's going to look into the implicit scope. So let's, this is what happens at the beginning, everything that is available without a prefix. I can't find an implicit, I'll go looking into the implicit scope. What is the implicit scope? Is the companion objects of my types. So in the code we were seeing before, what did we have? We had employee, map, and ID as types. So I would go and look into the companion object of employee. Is there an implicit in there that can yield, so that can basically take an employee and transform it into a map? If I can find it, I'll apply it. Otherwise, I'll go into, we said map and ID, I'll look into their companion object. And since map is a compound type, I won't just look into the map companion object, but I will also look into his superclass companion object. So in this case, seek companion object, iterable companion object, and so on. So as you can see, implicit resolution, it's a recursive algorithm, and it can be quite expensive, right? So what should we do when it comes to reducing our compilation times? Well, the one tip is limit the implicits that you have in the scope. The less implicits, the less work the compiler will do. So you should definitely avoid having imports with a wildcard that import basically whatever that you have no control over. Also because, maybe today there are no implicits in that wildcard import, but who knows about tomorrow? You have no clue what you're importing. So you should really try to avoid wildcard imports. And so where should you put your implicits? Well, you should try to move the implicits from the current scope into the implicit scope. So you should try to push basically the compiler into, look into the implicit scope instead of having too many implicits available in the current scope. And, as a proof of that, when we were at this project at Zalando, just by moving some of the implicits that were defined in the package object, so implicits in the package object are part of the current scope, right? They're available for all classes in the same package without any import. By moving some of those implicits from the package object, so from the current scope, into the implicit scope, we got a 40% compile time speed up on their project. Just by doing that. It was like, literally, it was like 5 lines refactoring. And it really didn't change the way they were working. They really didn't change the way they were, writing code. And, when we showed them that, it was like, oh yeah, of course we want to do that. It just happened to be that way, but we didn't realize it was that bad. So if you're interested in reading more, they actually wrote a report about the work we've been doing there, and just go ahead and read it up. So what about macros? Well, macros can help us reduce boilerplate, right? We love that. The less we write, the happier we are. But the problem with macros is that they can be responsible for 80–90% of type checking time. It really depends on how the macro is implemented. So you'd really need to go and understand what the macro does to understand what is the cost that you're actually paying at compile time. And so I would say you should be pragmatic in the way you rely on macros, in the sense that sometimes you're actually better off maintaining some boilerplate code. Just because, yes, it's beautiful, but you're basically hampering your productivity and your whole team productivity because you don't want to see some code in your source file, which potentially might actually be fairly simple, and there is really no need to use a macro behind the scene. So I'd say really be pragmatic. So it's pretty simple, isn't it? Of course not. If you guys, I definitely agree with you. If you think it's too complex to, having to do all these things, it's definitely going to take time. You have lots of guests to do, and there is lots of detective work. Complex. Well, Hydra can help you with that. Hydra will help you automatize all this process so that you can focus on your code and you can avoid introducing regressions. That's one thing. And Hydra will also help you just compiling faster by utilizing all the different cores. So let's talk about Hydra, what we do at Triplequote. So the idea of Hydra was to have sort of 3 layers. One is distributed compilation, both locally, so that we scale up, and both on different machines, so that we can scale up. And of course, the idea is that, well, the more power you have available, the faster you can compile. Another important thing is that it should be transparent. It should just really integrate with your tooling, with your development environment. You shouldn't notice. You shouldn't do anything different. It just works. And last but not least, it should be insightful. So all these things I've been talking about, you shouldn't be doing. There should be a tool that does it for you and just tell you, hey, be careful. You're about to commit something that is going to regress your compilation times. Right? We have monitoring at runtime. Why shouldn't we have the same for compilation time? Since we do have a problem in the Scala ecosystem when it comes to compilation. That's basically what we want to do with Hydra. That's our vision. So distributing compilation, I'd say it's a pretty natural thing to do. We all thought about it. But of course, there are some hard problems. So one of them is, well, what happens when you have different source files that depend on each other, but gets compiled by different workers or different machines? That's tricky. And the other thing is just inherent to the fact that we're building a distributed system. It's not easy, right, to build a distributed system. So, there are definitely some challenges. But, before we get into this journey, let's consider what is the speed up that we can obtain if we have something like that. What is the maximum speed up that we can achieve by having something like that? And Amdahl's law can help us with this. So P is the percentage of parallelizable work. So in this case, ideally, we want P to be as close as possible to 1. And S is the speed up for parallelizable work. So S is basically the number of cores. So ideally, we would like to have S tending to infinite and P as close as possible to 1. If that's the case, basically, we have infinite parallelization. The more we add, the faster we'll get. It's linear. So let's see some numbers. Let's say we have 50% of the work is not parallelizable. So what is this not parallelizable work? Well, it's work that has to be redone in each of these different workers. And when it comes to compilation, well, it means there are things like JIT compilation. JIT compilation will have to happen on all different machines or cores or threads. And there is memory bus contention. That is a cost that we will pay on each worker. There is penalties for these interfile dependencies because we need to know things about files that we're not compiling, but we need to we need some information to type check our own source files. So there is some work that is basically has to be redone on each of these workers. So if we have, 50% of this work is not parallelizable, the maximum speed up we can get is 2x, right? We cannot get more than that. And if 10% of the time the work is not parallelizable, then we can get 10x, which is pretty good. Wouldn't you be happy to compile 10 times faster your code? Of course you would. But, S, so the number of cores that we have available, is not infinite. So let's try to bring this table into something that maps into our laptops, our desktops. So we have 4 or 8 cores. So what is the speed up that we can look at? Well, you see, the number goes much lower. Like if you have 10% of the work is not parallelizable, we no longer have 10x, but we have 3x on a 4-cores machine, or we have almost 5x on an 8-cores machine. But that's still pretty good. I mean, if we can compile 3 times faster, if you look at the Scala team, what they're doing with their work on benchmarking and improving performances, right now we're talking about maybe 15–20% improvement. So we're talking about like 1.2x. So if you can get 3x for free, I'm sure you'd be happy. And this is exactly, so the yellow box is exactly what we're looking at when we use Hydra. Of course, it will depend on your project a bit, how much is the non-parallelizable part of your project. And based on that and the number of cores, you will basically see between 2 and maybe even 5 times speed up when you compile your project. So where are we today with Hydra? Today, we decided, well, first, we want to utilize all the different cores. So distribution will come later on. First, let's distribute the work across the different CPUs. And the granularity at which it works is the source file, also known as the compilation unit, if you look into the compiler naming. And we parallelize all the phases. So, basically what happens is that we take your source files, we split them up in some intelligent way so that we minimize these interfile dependencies, and then we assign it to different workers, and they just go and compile it. So what are the problems that we faced when developing this technology? Well, one is these interfile dependencies that I mentioned before. This is definitely a challenge. And the other one is that if you had the chance to look into the Scala compiler, well, the Scala compiler is not immutable. It's not an immutable compiler, the implementation. It's actually laziness and mutable state in the compiler. So that means that the moment you start parallelizing, if you have mutability, you got to be careful, right? So our approach was to start first with a shared netting, let's say, architecture. So we just had different compiler instances, and we would really just redo all the work on all these different instances. But that doesn't really take you that far, of course. So we had to sort of bring back shared state in a controlled way, so that we could actually get good speedups, and this is what makes it work today. So let's have a look at the numbers. So those are a couple of projects, open source projects, with and without Hydra, Specs2 and Shapeless, some of the modules there. We can see that for Specs2, we get over 2x compile times, while for Shapeless, I mean, it's not bad. We get more than 30% improvements, but maybe, of course, it would be better to get even more. But what we were really interested is to see, okay, but let's see how would an application that uses Shapeless work. And we thought that test for Shapeless could be representative of such an application. So let's see how Hydra behaves with Shapeless test. So that's pretty impressive on the red, the red bar for Hydra. And in case you can't make it up, it means 3 times faster, just compiling Shapeless test. Which, of course, this is the kind of speed up we want to be happy with, and we're gonna, there are plenty of things that we have in mind to make sure that we can bring up to 2x, 3x, also compiling source files, not just, well, main source files, not just tests. Even in the case of Shapeless, there are things that we can do. Right, this is a really good point. So all these experiments were run on this machine, which is a late 2013 machine, i7, with 4 physical cores, 8 multi-threaded, and all experiments were run using 4 workers. So that's good. So what I showed you before were warm compile times. But let's also see how Hydra behaves with a cold compile. So when you want to compile your code on the CI, of course you want it to be as fast as possible. And again, this was the result with the Zalando project. So the first compile is the call compile. And as you can see, Hydra, the red line, was actually faster with a call compile. It was faster than vanilla Scala after the JVM was worn, which is, that's really good. That's definitely important. And so you benefit not just when you're doing development, but also when you're building, when your build server is building PRs so that other people can get feedback about what you're doing. Good. So what about insights? So what about all these things that I told you in the first part? Well, we want to make those available in Hydra. Hydra will basically monitor your compile time, aggregates compile time, and also source file compile times. It will, with the idea that it should prevent you from committing something that will actually bring a regression with regard to compile times. And I mean, if you think about it, even when you bump the version of a library, you might actually get a penalty compile time-wise. So having a tool that can prevent those kind of regressions will help you, and it will help the community as a whole, just to keep an eye on what's happening during compilation. So basically, all the things I told you at the beginning, we don't want you to do it. We'll make it so that the tool does it for you. And finally, transparent, right? It should just work. And this is exactly how Hydra works at the moment. It's an SBT plugin for the moment. It doesn't mean that we can't support other build tools, but we have to focus on something, and SBT is the building tool that is used by everyone. You just add the plugin just like you would do for any other plugin, and that's it. You compile, and the only difference is that it will take less time, but nothing else will change. You don't have to do anything in your build. You don't have to change anything. So there is really zero risk in using it, because if it, for some reason it doesn't work, since it took you 2 seconds to enable it, it will take you just 2 seconds to disable it as well. And at the moment, we support 2.11.8 and later, and 2.12.1 and later. Of course, we're open to support other Scala versions if there is a need, but at the moment, it doesn't seem like that's the case. So what about present and future? Right now, Hydra is available. We're basically in this private rollout, so we're engaging with organizations that are feeling the pain of compile times. Of course, because we're still hardening the tool, making sure that it works really well. And there is no better way than actually having a strong relation, a strong collaboration with an organization that allows us to see what's happening and tune the tool and kind of understand how we can even get better speed ups. And at the same time, we're working into these insights and metrics. And in fact, next week, we're going to have a new release that starts adding these things to Hydra so that it makes it available to our users. But in Q4, so I'd say, anytime between September and December, it really depends on how the private rollout goes, we will be in general availability. And the idea is that Hydra will be available for free of charges for open source development. So we definitely want you guys to benefit and use it, and ideally be our advocates, and go back to your company and say, this is really cool, we want to use it. So not just during development, but also when you develop something at your company. And once we reach general availability, the next thing will be to work into distributing your build, so that ideally you can have compilation at your fingertips. You can decide how many cores, how many machines do you want, how much fast you want to get. For instance, that could be useful. Let's say you want to cut a release, you really want to go fast, then let's use as many cores as possible so that we really get to production as soon as possible. So with that, I'll conclude. If you guys have any questions, I'll be happy to take them. I put a link again to Zalando, as I think it's a really interesting report written by Eric Torrebore, so the author of Specs 2. And it gives you sort of an idea of the work we've been doing with them. And if that sounds interesting and appealing, and you'd like to have us maybe on site to work with you, please get in touch. We'd be happy to help you as well.
Thank you for the talk. I have a small question. So do you support Typelevel compiler?
Very good question. So at the moment, the way Hydra is, let's say, built underneath is a fork of the compiler. Okay, because we had to go quickly, we had to create this tool. So the easiest way was to fork the compiler and basically do whatever it was needed to, make it work in parallel. But our plan is definitely to unfork. And so, since the compiler is has this phase architecture, has many phases, we can just replace the phases that we need. And ideally, at that point, we're going to be supporting the Typelevel compiler as well. Of course, that's also based on, I'd say, commercial needs. Because, of course, there is, maintenance and everything that goes with it. But we did have one organization that was interested in using the Typelevel compiler, so I'm actually confident that we'll get there. Also because the Typelevel compiler isn't really that much different from the Scala compiler, so it shouldn't be much of any work to support both.
Really cool. Is anything that you do on Hydra open source?
So at the moment, we're going to open source the SBT plugin we have. But the core, which is Hydra, so it's the compiler is where, let's say, the secret sauce and all the magic happens, that is going to stay closed source because we want to build a commercial entity, of course. But, we have this belief that if the tool is free of charges for open source development, it should be, let us know. But to us, it feels like that's a really good compromise between building a commercial entity and so basically building a business. And on the other hand, making sure that the open source community can benefit and can actually compile faster.
Does it mean that it's only SaaS provided?
I didn't get that. Sorry, I'm not.
So does it run behind firewall, basically?
Oh, that it's a bit too early to say. We'll have to see what it means exactly. But I don't have an answer to that at the moment. But Hydra, you'll be able to download it just like any SBT plugin. Of course, you'll have to sort of agree to the license and terms, meaning that you use it for open source development, but there shouldn't be any other constraints. If you can use SBT behind a firewall, you should be able to use Hydra as well.
Hello.
Hey.
As you said, you have to be very careful not to parallelize the parts of the compiler that are not parallelizable, so they depend on mutable state.
Right. Correct.
Does that mean that every time a new Scala version goes out, you have to update or test, and if needed, update Hydra to adapt to the new Scala version?
That's a very good question. Yes. So at the moment, what it means for us to support new versions of Scala means that we need to apply all our changes to this new version. Of course, Scala versions don't happen every 2 weeks. So, it's not really a burden at the moment. And as I said, our plan is actually to unfork and then have phases, which will be a lot simpler to just, maintain and apply on different, But at the moment, every time there is a new compiler version, we're going to release a new version of Hydra. So you as a user will never have a problem with it.
Okay, and still regarding mutable state, do you handle macro implementations conservatively? Because in particular in Shapeless, there are a lot of mutable state private to each macro. So you could get different results if you run a macro in two different instances of the compiler.
So what we guarantee is that we produce identical bytecode as the vanilla Scala compiler. So you will actually get the same bytecode, so the macro expansion will be the same, and we guarantee that. And in fact, another thing I didn't mention is that we're going to be using the Scala community build to validate what we do. Of course, we're already compiling most of the project in the Scala community build, but we're actually going to use the exact same infrastructure so that I'd say we're as good as vanilla Scala when it comes to testing Hydra.
Hey, Mirco, great talk.
Thank you.
Will you support Dotti?
So, Dotti is definitely one of these things that we would like to get to, just because it's exciting, this whole new compiler. We haven't done any work on it yet, but I think it could be a very interesting research R&D project, since we're very close to EPFL. we can get a student, an intern working on it. Maybe not this year, it might be next year. But I really don't see any reason why we shouldn't be able to do the same. The architecture of Dotta is not that different. I mean, there's still phases. There's still type check. It's pretty much similar, at least at the eye level. And Dotta would also benefit from being able to parallelize compilation. So yes, it's definitely on the list. Maybe not at the top, but it is on the to-do list.
Okay, so if there are no more questions, you actually did finish 10 minutes before time. I have two advices, I guess. One is free, one I will charge for. So first, the free one, don't turn on your warning builds if it's not a CI, because it does slow down the compiler.
Right.
It added like 4 to 5 minutes to our builds if the warnings are enabled. So when you're doing like a production build that you're not going to read the warnings for, don't do that. So you said on CI, so that's
yeah,
good.
I say on the CI. I don't know if the overhead is actually that much. But you can easily check. I mean, just run it once and you see whether what's the overhead, and then you decide. It's your decision.
And the second one for Triplequote is that you should do, you should get the 10,000 more popular Scala repositories, and then do a single PR that adds the line, and then just do a comment like this will speed up your build by 2.3%.
Right. And I think when we get there, that's exactly what we're going to be doing.
So expect some spam from Triplequote people. Okay, put your hands together and can't wait to see it in action.
Thank you, guys.